Hello everyone and welcome to another Stat 437 lecture video. In today's video we are going to be talking about discrete time to event data. So we're going to be building off of sort of the quantities that we were talking about in the last lectures, and we're going to be looking at them specifically in the context of discrete time to event data. So it's going to be survival analysis when the outcomes happen to be discrete times. So we're going to sort of walk through conceptually what we're trying to do when we have discrete time data. And then in the coming lectures, as we've been doing, we'll take a look a little bit more detail at the theory of it, and then we'll do some implementation inside of R. So today we're just trying to get all of the ideas out there, and then we'll see these ideas again another couple of times as we work through the theory and the application. So to begin with our introduction here, I want to start by discussing a brief example. And so this is an example. These data are available on the course website here. And what we're looking at are the employment data for teachers from this survey that was trying to understand teacher turnover. And so each one of these bars is the sample for the number of years that a teacher was actually employed. And you can see that we have these coloring where we either have these red or these blue bars. And the red bars indicate teachers who ended up leaving their job, so we observed an event for. And the blue bars indicate teachers who did not leave their job, but who were still working when the study ended. So for the blue bars, we're thinking of those as teachers who had their times censored. At some point in the future, they're going to leave their job as a teacher. We just don't know when that is because we stopped following up with them. And so you can see I just have some random sampling of all of the teachers in the data set here. And my point with doing this is sort of illustrating the type of data that we want to start thinking about when we're talking about discrete time to event data, right? So you can see the range here is teachers leaving somewhere between 1 and 12 years. At 12 years was the maximum a teacher could have been followed for. And the way that this study actually worked was they started the study in a year, and they had planned to follow that group for 12 years. But any teachers who started after that first year, they were followed as well. And so you can see that we have this second individual here seems to have been censored after 7 years. And so what that really means is that they started 5 years into the study. And so you can see that we're defining the baseline, this time 0, as the time that the teacher started working, but the study itself actually, that would have been 5 years into the study. And so again, this is just trying to serve as an example for sort of how broad the types of questions that we can try to answer with survival analysis are. But what I'd really like to be able to do by the end of today's lecture is to characterize this survival distribution. So it's a fairly manageable discrete distribution. How can we think about the hazard function? How can we think about the survivor function? And how might we be able to characterize measures of central tendency? So in general, with discrete time survival data, the idea is that we're going to observe some time, TI, for each individual. And what we're going to do is we're going to discretize it. So if it falls in the interval between k and k plus 1, we're going to assign it the discrete value of k. So, if we're thinking about the teacher example here, if a person quits in between the second and third year, somewhere in that time, then we're going to sort of assign the event time as 2 there, right? And so there's this really natural way, a lot of the ways that we think about counting time, we sort of are already doing this when we're talking about it. If we count something in years, right, we're probably already sort of rounding down to the nearest year. And so there's a lot of problems where it makes sense to think about sort of on this scale, and that's how we might be able to do that. And so our goals of the analysis here are going to be first to estimate the hazard function. Next, we want to estimate the survivor function. And we also want to be able to characterize the measures of central tendency. And finally, we're sort of going to wrap this up in terms of a likelihood-based analysis. Okay? And so hopefully you remember sort of all of the definitions of these quantities of interest here. If not, I'd advise you go back and take a look at the last lecture. But these are the quantities that are sort of going to be sitting at the heart of the survival analysis that we do. So to begin, let's start talking about the hazard function. As a reminder, the hazard function is the probability of an instantaneous event. So it's the probability that the time equals t, given that we know that the time is at least t. Sort of thinking about it as what's the probability that an individual has an event in the next moment, right? In the discrete time case, this is an easy thing to wrap our heads around because the probability that t equals t actually has a meaning. It's a little bit harder to work out in the continuous time case, but we're thinking about this as sort of we know this person is still at risk. What is the probability that the event happens in the next interval of time here? So what's the probability, after 3 years, if we know that a teacher is still teaching after 3 years, what's the probability that they quit in this upcoming year? And so we want to figure out ways to try to estimate this hazard function. So if we suppose that at time k, we have some number of individuals that are at risk. And so I'm denoting the number of individuals at risk at time k as rk here. Then we can think about also counting up sort of the number of individuals who actually experience the event there. And we'll denote this with dk, right? So we're looking at some time period k. At the start of time k, there are still rk individuals in the sample. So that's rk individuals who have not yet had their event and who have not yet been censored from the study. And then we observe dk of them to have the event there. There's this obvious estimator that we can look at, which is to take the ratio, the number of people who have the event divided by the number of people who are at risk of having that event, right? This is sort of exactly what we did with the transition probabilities, where, we were looking at how many people were transitioning at any given moment. And it's the same idea here, where, we're thinking about how many people go from being in our sample at risk to having had the event happen. Okay, so this is sort of our obvious estimator. And this empirical proportion of those who are at risk of experiencing the event, out of the total people who could have sort of had that event happen to them. And it's this really nice intuitive idea of capturing the hazard function, and we've accounted for censoring implicitly because we're only considering the people that are still under observation at the time, right? So this is sort of going to be the base of our discrete estimation here, is this nice estimator for the hazard here, for that instantaneous probability of failure. And it's the same probability we were looking at in transition models, and so maybe that gives you sort of a hint that this is probably also coming out of a likelihood type analysis. Now, oftentimes we're going to be presented our data sort of in a life table format here, right? And so what we're looking at is we have the sort of 12 years of study. This is for the teacher's example. And at each year, we have some number of individuals who are still at risk. So this is the number of people who have not yet been censored or had their event happen. We observe some number of events in that year. And then we also observe some number of individuals who were censored. Then from that, we can actually compute our estimated hazard function. And the way that we're getting the estimated hazard function is we're looking at the number of events, and we're dividing that by the number who are at risk, right? And then the number who are at risk in this next year are going to be given by the number who are at risk in the first year. We're going to take off the number of events that are there, and we're going to take off however many people are censored, right? So the first handful of years down here, it's just going to be the difference between the number who are at risk and then the number of events we observe. But once we actually start censoring individuals, you can see this 2045. If you take off 123 and you take off another 280, well, that's going to give us this 1642 here. And so the idea is that we can actually get this estimated hazard function directly from this life table. You don't need to actually see the data itself. We can get sort of everything that we need to know directly from just the counts of individuals, which again sort of harkens back to what we were doing with these transition models. And so hopefully these types of tables are clear for how we might go about working with them. And I'd advise you to sort of pause on this slide, download the slide from the course website and take a look and make sure you understand where all of those numbers are coming from. But this turns out to be a fairly powerful tool for estimating the hazard function here. So if we have this hazard function, the next obvious quantity that we might care about is the survivor function, right? So If we wanted to try and take that similar intuitive argument that we just made for the hazard function, we could try and do the same thing for the survivor function. And we could say, well, at time k, we said there are rk individuals left. We knew we started with n total individuals. And so rk over n is the total number of people who are surviving at time k. But this is not going to work, or at least not generally. And the problem is censoring. The general issue that we're having here is we're not differentiating the people who left because of an event or the people who left because of censoring. And so this would work if we had no censoring, right? This is going to give us the proportion of people who are remaining, and that's sort of an intuitive, a sensible estimator for the quantity we care about. But if lots of people are being censored from our study, we're sort of going to be overestimating how many people have left, right? And because of that, this estimator is not going to work. But if you do remember, we discussed this relationship between the survivor function and the hazard function. And in particular, we said that the survivor function is equal to the product of 1 minus the hazard function up to the time k, right? And so this right here, this relationship gives us this really interesting idea. What if we just took the hazard function that we've estimated from the data and we plugged it in here, right? We just used a simple plug-in estimator. And so if we do that, we get this really nice form that, again, is just computable from those life tables that we were looking at, right? So we take the product from j equals 1 up to time k of 1 minus dj divided by rj, where this dj divided by rj right here is just the estimated hazard at time j. Okay, so it's sort of just this cumulative product of 1 minus the hazard function. And that's going to be how we estimate the survivor function in discrete time data. We're just going to exploit this relationship between the survivor function and the hazard function, and then having estimated the hazard function is doing all of the work for us there, right? So it's this fairly simple way of using those relationships between the quantities that we care about in order to get good estimates out of them. There's going to be other ways you could think about doing this, but this is sort of a nice non-parametric way. We've not made any assumptions, and it's going to work really well in general. So if we have our hazard function and we have our survivor function, we also want to be able to discuss measures of central tendency. Okay? And the problem that we're going to run into is that we can't sort of take sample means. The means are going to be biased downward. Now let's try and think about why that's happening, right? So if you just take the mean of the amount of time that someone was in the study, well, you have to start thinking about how do we handle people who were censored, right? And the problem is that we know if you just record someone's censored time as part of their mean, well, by definition, when they're censored, the event has not yet happened. And so if you want to know, what is the average length that a teacher teaches, right? If we take the people who are censored at 12 years, well, those people have actually taught for longer than 12 years. And so if we're just including that value of 12 there for them, well, then we're going to be biasing the mean downward. And so you might say, okay, well, what if we only looked at the individuals who actually we observed an event for, right? What if we ignored anyone who was censored? The problem that you're going to run into there is that you're sort of running into this selection bias problem, right? Because if you're only including people who weren't censored, well, you're going to be looking at the population of individuals who, again, by definition, had their events happen earlier on. And so again, you're going to end up with a biased downwards mean. So sample means, as we tend to think about them, just don't work when you have censoring in your data. They're going to end up being biased. And so this non-parametric version of mean estimation, just being able to do it without sort of imposing some sort of structure, is not going to be possible. Whenever we can't use the mean, we think about using the median instead. And the reason that the median is nice is because we know that we can express the median in relationship to either the survivor function or the CDF equivalently, right? And in particular, if you think about what the definition of the median is, it's going to be that value such that half of people are below it, half of people are above it. And so we typically define this with respect to the CDF, but for the median, the survivor function is going to work just as well. And so as a general rule, what we're going to do in the discrete case is we're going to find the value of m such that our estimated survivor function is greater than 1/2 at m, and it's less than 1/2 at m plus 1. So it's the last value of m before you've crossed over sort of the 50% threshold, right? And then to actually estimate the median from this, we sort of just do this linear interpolation here, right? Where we take that value, and instead of just calling that our median, we're going to say how far off of 50% is it, and then divide by the slope. This is really just an interpolation correction. It's the type of correction that you would have seen in your intro stats courses when you're sort of using a linear approximation here. But the basic idea is that we can sort of get this median just from that estimated survivor function. Okay. And so what I have here is the data from the teaching example, and we had already seen the hazard function being computed, right? And so we can think about doing the survivor function. And we remember the survivor function is being estimated as 1 minus the hazard function, and then you take the cumulative product, right? And so you're going to have this 1 minus the hazard function here, and then you're going to multiply by 1 minus this to get our value here, and then times by 1 minus this to get the next value, and so on, all the way down. And if we start just peeking into the values over here, and we wanted to start thinking about what's the median going to be, well, if we take a look, when m equals 6, we have this survivor function estimated to be 0.51, and when m equals 7, we have this estimated survivor function below 0.5 at 0.487, right? And so we're going to take that small m value to be 6 in this case, because it's the last value that's above 0.5, and then we would just need to apply a little bit of a correction. So it's going to be somewhere between 6 and 7, somewhere around 6.5, just trying to eyeball it right here from this data. Okay, and so all of that, the nice piece for what we've been doing so far is that we've done this entirely from a non-parametric point of view, right? We've sort of just taken that one estimator for the hazard function, and we've been able to, using that, derive all of these other nice properties to characterize the distribution, the survivor distribution for what we might care about. Now, we can sort of apply a little bit more formality to this through the use of some likelihood theory. So just like with transition models, we defined a stochastic process. We can do that in the survival analysis context. So what we're going to say is that ys is going to be this process here, where it takes a value of 0 or 1, and ys0 means that the event has not yet occurred, and ys equals 1 means that the event has occurred, right? And then we index over discrete time, s equals 0, 1, 2. So again, all of this should sound fairly familiar from when we were talking about transition models. And if you think about why that is, well, we're sort of using a transition model here, right? At some point, you're starting in the place where no event has happened, and at some point, we're going to transition to the event having happened. So it's this two-state transition model, which really is going to motivate how we think about doing these discrete time processes. Now, in addition to the event process, we want to define a similar one for censoring. So we define ZS to be a stochastic process, again, in 0 and 1. And the idea here is that we're going to start ZS at 1, and we're going to keep it at 1 until they're no longer under observation, right? So once an individual has been censored, ZS is going to be made to be 0, right? So we start YS to be 0 because no event has occurred, and we start ZS to be 1 because they're not yet censored, and we run both of these processes alongside one another. We're also going to, as before, define these history vectors, right? So I have this fancy H with a Y superscript, and that's just going to include all of the states up to time s-1. And then we could also do similar notation with the process for the censoring process and the joint process as well, right? So it's just the same notation being extended out there to capture all of this history. Now, for any individual, we're interested in looking at their likelihood contribution, right? So the likelihood contribution for individual I, and you can think about this as being sort of this joint distribution between ys and zs, and we're going to be conditioned on the history, right? And what that's going to give us, or sort of this conditional distribution, if you take the product of it, that's going to give us the total likelihood contribution, the total joint likelihood contribution for the individual, right? And so we can actually expand this out a little bit and instead write this first term as the conditional probability of the event process given the censoring process, and then we multiply that just by the conditional probability of the censoring process, right? So this is just sort of the standard manipulations here, and we'll see this in a little bit more detail in the next lecture. But the idea is that we're looking at similar probabilities here to, or similar likelihood contributions to when we were looking at our transition models. And then we think about making two simplifying assumptions. So the first is that we want conditionally independent censoring. And so under conditionally independent censoring, what we're saying is that if you take this probability of the event process and you condition on both the history and the state of being censored or not, that's the same probability as just conditioning on the history. So knowing that the event has not happened up to time s minus 1, the censoring process gives us no more information than that, all right? And so this is typically actually a fairly reasonable assumption if what we're thinking about with censoring is sort of administrative censoring, right? If we're thinking about we're going to run that teacher study for 12 years, well, knowing that they're still under observation does not really tell us anything other than the fact that they haven't left the study. But we already know that through this conditioning on the event process here. Okay, so it's the conditionally independent censoring might not always be valid, but it is a fairly reasonable assumption to work from. We can also think about making a non-informative censoring assumption. And the idea here is that we have our censoring process, so that's the ZS, and we also have this event process, YS. And the idea with non-informative censoring is that they don't share parameters. Okay, so we need this probability, this conditional probability that the individual is being censored, we want that to be independent, functionally independent of this probability that the individual has their event. Okay, so they're not going to share parameters there. And again, that normally makes some level of sense because the event is sort of independent from the reasons that someone might be censored. Now, this conditionally independent censoring is a really important assumption for what we're about to do. The non-informative censoring assumption, less important for what we're about to do. But if we make both of these assumptions, then we can see that this likelihood actually simplifies down to just the product of these conditional probabilities here, right? And that's because we can drop off that term, the second term, if we make the non-informative censoring, and this first term simplifies based on the conditionally independent. But the nice part here is that we can actually write this out in sort of a nicer way with respect to the parameters that we care about. So if we take just the product instead of s equals 1 to infinity, if we just go up to whatever time the individual is going to be censored at, and we can treat that as fixed because we know that censoring is not impacting our process itself. So even if it's random censoring time, we can treat it as fixed because of that non-informative censoring, right? And so the idea here is that if the individual had their event happen at time s, well, then we know that the probability, this conditional probability here, is exactly the hazard function. That's what we've defined the hazard function to be. And if they didn't, well, then it's 1 minus the hazard function because that event did not occur, right? So we get this really nice expression where what we're doing is we've boiled down from looking at the stochastic process notation into this hazard function notation here. And so if we just specify some type of parametric model for the hazard, we get this really nice simplified likelihood. And so we could actually work from these parametric models for the hazard here as well. And then I asked the question, does this look familiar? And the reason that I asked this is because this is going to basically be a binomial likelihood problem. This is essentially what we were dealing with the transition probabilities as well, right? And so, does this look familiar? Well, I hope so, because this has come up not only in this course, but probably beforehand as well. And so, we've done a lot of work to sort of build out our transition models, to build out these discrete time survival models, but they're functionally the same thing, okay? And so that's essentially all of the topics to cover for discrete time survival analysis. Now, I know we've gone through them fairly quickly, so I'll summarize them here, and then, we'll see in sort of more detail all of this information. But, from a high level, working with discrete time survival analysis is essentially what we were already doing with transition models. But to sort of wrap this all up, if you want to discretize the time, then we can use discrete survival methods. all of the information that we care about for getting our estimates can come from life tables, right? So if we summarize with the life table, we can get the estimates of the hazard function, we can get the estimates of the survivor function, we can use those to get an estimate for the median as well. The survivor function, we exploit that relationship it has to the hazard function in order to estimate it correctly. And then the median is the estimate of central tendency that we use because the means are going to be biased. Now, there is a way that we could use the means, which is by imposing a parametric model on it and then computing an expected value through that. But this median value is going to be totally non-parametric. It's not going to rely on what we're specifying. It's sort of always going to be valid. So we like to use that. If we exploit that same stochastic process notation that we were using for transition models, then we can get out a likelihood-based expression. And then under the assumptions of conditionally independent and non-informative censoring, this has just become a binomial likelihood, right? And so the binomial likelihood, why do we like that? Well, we like that because we can use GLMs to fit it. We like that because it's what we were using with transition models. It's what we're used to using, throughout statistics as well. So this problem that might seem, fairly complicated, how do we deal with discrete time survival analysis? It becomes the question of, are you willing to accept conditionally independent and non-informative censoring? And if so, now you're just working with binomial likelihood data. And when we're working with binomial likelihood data, well, we can use GLMs, we can bring in covariates however we want through that process, and it becomes this really nice place to work, a place that we should be quite comfortable working within. So that's essentially everything that I wanted to talk about from this conceptual lecture. In the next lecture, we will sort of dig into this in a little bit more detail, and we'll see it applied and through the theory. As always, if you have any questions at all, please feel free to reach out to me. And otherwise, I will see you all in the next lecture.